Okay, let's get started with RELION. Now, RELION is one of those softwares which takes a little bit of time to get used to, and there's an excellent tutorial for this on Google. So just Google RELION 5 tutorial and it'll pop up. So go and grab that, and that will really help you process your data to its full extent. I'm only showing you today how to get set up. What I've done is created a sort of Scratch project, which is accessible by anyone in Curious, which should be you. The way you can access this is by going to all the way up to the top directory from this file system, going into Scratch, project, scrolling along here to find Farah_workshop, and this is what you'll see. So you can copy these, you can't write, but you can copy. What you'll see here is around 2,000 Apopheridin movies which were collected on the ARM 300 by Lou at CMM. So these are excellent to practice with. And if you go into here, you'll see a number of different folders. I've got this all set up for this workshop. What this 200 is I've just taken 200 movies from here and popped them into here to make this all a little bit easier for today. So we're just going to work on 200 movies. So you've got this open. I want you to open the Scratch in which you want to work from today. Then I want you to just grab all of this and copy it and paste it into your Scratch. Okay, I want you to pretend like I've done that into my Scratch, but I'm just going to work straight from here because it's good practice not to have multiple copies of the same data floating around. But you'll have to work from your Scratch. Let's get started. Pop up to the applications up the top here, navigate to RELION 5, and RELION launches as a terminal. Don't be scared. It is not long. You have to deal in the terminal, but the way RELION operates is it works from one folder. It doesn't like to come in and out of its folder, so just make it a fresh folder. That's what we have here. And make it a fresh folder, and that is where it's going to live. So when we start up RELION for that specific data set, it will always be that data set that it finds. So each time you have a new data set, make a new folder, and that will be where that RELION lives. Let's get it to where it needs to be. CD to your folder. You can drag and drop into this window, or you can write all this out, whatever you prefer. Press enter, and now you'll see that we are in the correct directory. The other thing I want to mention is because RELION doesn't like to come out of its directory, I have made a symlink to the 200 movies in here, so it doesn't have to come out to find them. But you can also just as easily drag this and make it live in the RELION folder. So once we're in the correct directory, all we need to do is type RELION and press enter. And there you go. This is what RELION 5 looks like. And the first thing we want to do is import movies. Yours will pop up and it will say something like micrographs asterisk TIFF. What we want to do is change this to our specific data set. So like I just said, ours is called 200. Then you'll have dash asterisk, which basically just says, I want you to go to the 200 folder, and then everything that's a .tiff, that's what I want you to import. So that's what this asterisk means. Everything which has this will be brought in. Now, are these multi-frame movies? Well, how do we know? So if we go to one of these info text files, double click, you'll see a bunch of information about how this data was collected. And if we just quickly scroll through here, ta-da, this is in fact a 40-frame image. So are these multi-frame movies? Yes. We'll leave this as optics group 1 and the MTF of the detector. So this is specific based on the type of detector used. So as you just saw in that text, the detector type here is a K3. So in order to get the MTF of the detector, you would have to navigate to the manufacturer website and either request to have this MTF file sent to you, it's a bit of a hassle. So I have actually made one for the K3 and the ARM200's K2 just available for you. So please feel free to grab these and use them whenever you need, because again, they are a bit of a pain to find. So let's import the K3 one, which is the correct one for this dataset. RELION is okay with going up one folder just for a small file like this. So let's tell it where to find it. The pixel size. Again, we can look at this file and we can see that the pixel size is 0.8. Or we can look at the other file to see the same thing. So if we look at the mdoc, you'll see that there's even more information here, and it does tell you the pixel size just down here as well. The voltage, so the voltage information will be on here up the top, so it's 300 kV. And the spherical aberration, so this is specific for each microscope as well, and as far as I know, we've been setting ours at 2.7. Others, you can leave all this as it is, and running, leave all this as it is. And what we want to do is just click run. You can see how fast that imported the files, and you can see that it's imported 200 items, which is perfect, because that's what we'd expect. Now the next step in RELION is to do motion correction. And what motion correction does is basically, when we collect the images, we usually collect them as about 40 frames. And the reason we do this is sort of two-factored. Firstly, the first couple of frames will be usually unusable because the protein gets so excited by the time the electrons sort of hit it that the data is not really that great. Then by the end of the 40 frames, the protein has been hit by so many electrons that it might begin to denature. So that's one reason. And then the next reason is you basically need to account for the motion that happens. So you have your initial frames that need to be taken out. You've collected a fair bit of good information in between and your last frames which you've taken out. But as you've collected those good bits of information in between, your protein is actually moved due to the excitation of the protein from the electrons and due to the ice changing composition as the electrons are also passing through. So you get ice melting and you get things moving around, and it needs to be corrected for. There are algorithms in place to do this, and that is what this job type is. You might find that your first and last frames are just fine, but it's also common practice to take those last couple out. Over here, what you want to do is double click here, go to your import job, and click on that to make sure it's importing the correct thing. You can choose to keep or remove the last and first frames. Then we have a few different options down here. Yours will look something like this, which is the default settings for if you are using RELION's implementation. So what is that? Well, we can either run this job CPU or GPU. It doesn't really matter. I mean, the CPU takes a lot longer than the GPU version. But if you're not in a hurry, then it really doesn't matter. It will do the job in a similar way. Firstly, I'm just going to show you that to do that, RELION's own implementation is the CPU version, but it's motion correct, which is the GPU version. And here we're using Motion Core 3. But before we get to that, you can adjust the number of patches that the system needs to use in order to correct for the motion. Then what we have here is very important. I'm not going to set it up today because I am just taking us through the basics, but as you're collecting data, you will get a gain reference image and a defect file. Now, these will be in here and in here. But what you'll find is you need to make sure that these are the correct format for the software you're using. Annoyingly, RELION and CryoSpark like to have these in different formats. and sometimes your gain needs to be rotated or flipped to make sense. This takes a little bit of playing around with, and it will be different for the two different types of microscopes that we use at UQ. Take some time to go through that and get it right, because you don't want to make it to the end of your data processing only to find that, oh, in the first step, I really should have got this correct, and then you have to start again. I'm going to take you through how to set this job up on a different node, or on the GPU that your desktop is currently running on. We're going to look at the GPU version here. In terms of which GPUs to use, you don't actually have to have anything here, but what this means is GPUs are actually numbered from 0, so you're allowed to use 3 GPUs on Bunya. So that means if you wanted to use all 3, this would be 0, 1, and 2 in terms of naming them. So let's just say we want to use 0. Then I want to run this job initially just on the GPU that my desktop is running from. And I want to show you how that job is running by popping open a terminal. I want to run the command NVIDIA SMI, and that is going to tell you exactly how the GPU beneath this desktop is running. But to have that constantly update, we need to add watch. So watch NVIDIA SMI. Press enter, and this is the lovely GPU I'm running from, which is an L40 GPU. And hopefully what you'll see is when I press run on this job that the amount of GPU utilization pops up. So I know that the GPU version can't use this or this, so let's go ahead and change those and click run. There you go. So you can see that the GPU utilization has jumped up from 0 to 100. So that's excellent. It means it's working. Motion correct is a little bit janky, so it'll jump around all over the place as it's running. Saying that 200 movies is going to take 23 minutes on an L40 card. You can imagine just how long this takes if you're doing thousands of movies. That's one way to do it. The other way we can do it, if we click on the motion correct job again over here, is to send this job off to a separate GPU. So we'll leave this running down here. I'm going to launch another terminal. Set this up here, and we're going to watch my queue. So what do I mean by queue? Well, if you aren't aware, Bunya works from the Slurm system, which is basically a fair share system to ensure that the resources of Bunya are utilized fairly across different users. That means because it's Slurm, a lot of these commands start with S for Slurm. And there's a whole lot about this on the Bunya GitHub page as well as online if you want to learn more. What I want to do is watch my Slurm queue. So I'm allowed 3 GPUs. So if I just again type watch as queue, so I'm looking at my Slurm queue, and -- me, you can see that I'm running one thing. And that one thing is this desktop. So I'm utilizing one of my GPUs to run this desktop. But I have 2 more GPUs, so I can actually send this job to a different GPU because we were quite smart with how we set up these desktops. We have allowed the desktop to be able to launch separate jobs, which is extremely powerful. So how do we do that? We are going to submit to queue. Our queue name here is GPU CUDA or CUDA, and this is what most of the cryo-EM processing has been optimized for. So we also have AMD cards, but again, this processing has been optimized for NVIDIA cards, and to access those, we need to ask for the CUDA part. So this will also be a sbatch command. Again, if you want to learn more about this, head to the GitHub. This account will be specific to the account you've been added to. So I'm in the Cater group at IMB, so mine is A_Cater. Then you have time of the job to run, memory, and GRES. So we haven't gone through GRES yet, but we can do so right now. The best way to sort of describe this is head to that cheat sheet. Down the bottom, I have some details about the GPU architecture. So there are 3 different types of cards on onBunya. There's the A100s and H100s, which are cards which are famous for doing MD or AI type of calculations. But they're also really good at running the jobs that we need them for as well. There's also the L40 cards, which are exceptionally good at visual feedback, but they're also quite good processing cards. And then there's this other one with a really funny long name. So these are basically A100 cards, which have been split or partitioned. So 2 of our A100 cards have been split into 16 little cards, or slices or splices of card. So the reason we've done this is because sometimes you just have a little bit of code that you want to see if it's going to work, or something you want to test, and that means you can test things really quickly because they're quite readily available. But of course they're limited because they've been split up, so they've only got about 10 gigabytes. But they're really helpful, and that's what we're going to use right now. Let's go ahead and copy this name because I don't want to write it out. And I'll take you through what each of these parts of GRES mean. So GRES has 3 parts. It's asking you, do you want this to run GPU? Then we add a colon. Then it's asking us what type of GPU. And I'm just going to say this long name, which is one of those sliced up cards. Then we add another colon. Then it's asking us, how many of those do you want to use? And I just want 1. Okay, that is all filled out. And what I want you to appreciate is how this actually gets sent off. I'm going to click run. You can see in RELION that job got submitted. So that's great. You can see over in my Slam queue, it's just landed in the queue. And because I asked one of those little cards, it got through the queue straight away. So you can see it running there. Then, because this desktop is all part of the same system, you can see that it immediately gets fed back to my RELION. So there you have it. That's how you set up things on RELION. Go through and run through the different job types, and thank you.